Hi, and welcome to our second video. We talked in the last video about what a variable is, what an equation is, what an expression is, and also how to check whether or not certain values of our variable are solutions to equations. We're going to talk now about a particular type of equation, the simplest type, a linear equation. So you can see here that a linear equation is any equation that we could write, and this word could is important. We could write it in this format. Ax plus b is equal to 0. Of course, also we might see it like ax equals negative b or some variation like that. But as long as we could write it like ax plus b equals 0, where a and b are just some real numbers, lots of choices there, just a can't be 0, we've got a linear equation there. So for instance, if we look at number 1 here, that's a linear equation. Okay, it's in the exact format that we expect. And if we wanted to solve a linear equation, you're experts by now at doing this, we could of course isolate the q. So what we would do is we would add 9 to both sides, and then we would multiply both sides by 1/7, or divide both sides by 7, however you like to think about it. Okay? And there we have a solution. Now of course you and I both know this is definitely the solution to that linear equation. But just to practice our format for verifying solutions, let's verify it over here. So the left-hand side would equal 7 times 9/7 minus 9. And if we do our fractional arithmetic, remember that's 7 over 1 times 9 over 7. And we can cancel out the common factor of 7 in top and bottom there. We get 9 over 1 minus 9, which is of course 0. Our right-hand side is also 0. So we found that the left-hand side is equal to the right-hand side. Thus, our q equals 9/7 is a solution. Now below we have another linear equation. Again, you're very familiar with how to solve these linear equations. We'll bring all the terms involving y over to one side by adding or subtracting as appropriate, and we'll bring all our constant terms over to the other side. Again, we're trying to isolate y. So we've got 4y minus 11y on the left. That'd be negative 7y. And if we add 6 to both sides, we end up with 1 plus 6, 7 on the right. So here, when we multiply by negative 1/7, or divide by negative 7, however you like to see it, we end up with y equals negative 1. Again, we can check and verify our solution. The left-hand side would be 4 times negative 1 minus 6. It'd be negative 4 minus 6, which is negative 10. Of course, we're pretty confident that y equals negative 1 is the correct solution. But again, we're just checking. On the right-hand side, we've got 11 times negative 1 plus 1. That would give us negative 11 plus 1. That's negative 10. And exactly what we expected. The left-hand side is equal to the right-hand side. Y equals negative 1 is a legitimate solution. So we can write our little conclusion. Now, this is very simple. And of course, it seems like a lot of overkill just to check our solution. We're just doing it for now to practice that, since it's a new skill, and this format that I want you to use is incredibly important. So I want you to practice it and be very good at it. However, in the future, we're going to solve a lot more complicated solutions, and there will be certain values that will show up for various reasons that turn out not to be solutions to the equation. So we do need to be very careful in checking it, and checking it will become an integral part of solving complicated equations. Also, of course, when you are solving equations on a test, you might want to know whether or not you got the solution or not. And so by checking, you can know with absolute confidence that you did get the right solution, or if the left-hand side and right-hand side aren't the same, that there is a mistake somewhere. So you might want to go back and find it. Now that's all we really need to say about linear equations for now. I want to move on to linear inequalities. So remember, for an equation, what it is it's a statement that says that one expression is equal to another expression. Well, what if the connection between the two expressions isn't exactly equality, Instead, we just want to say, look, the expression on the left-hand side is less than or equal to the expression on the right-hand side. So here we have an example where we've got 8x minus 4, perfectly good expression. We have x plus 5, another perfectly good expression. And we want to say not that they're the same, but just that the left-hand side is less than or equal to the right-hand side. And of course, there's 4 different options here. You've probably seen them all at some point in your math career. We can have strictly less than, which means they can't be equal. The left-hand side has to be definitely less than, strictly less than the right-hand side, and so on. Now, just like with an equation, for inequalities, we have solutions. Just like with an equation, we have a left-hand side and a right-hand side. And so to figure out whether or not a particular value of our variable is in fact a solution, well, we plug it into the left-hand side. Completely separately, we plug it into the right-hand side. We calculate those values. And then if the left-hand side and right-hand side obey the inequality, for instance, in our example, the left-hand side would have to be less than or equal to the right-hand side, then that value we plugged in is a solution to the inequality. Now, for linear equations, we usually just get one solution. But for a linear inequality, we might get lots of solutions. In fact, we might even get infinitely many solutions. Now, we'll talk in a moment how to find all of the solutions, but for now, let's just stick with the task of figuring out whether or not a particular value is in fact a solution. So here in our exercise, we're asked to figure out whether or not x equals 1 is a solution to that inequality. Imagine that someone we really didn't trust told us that x equals 1 was in fact a solution. Well, we'd be quite skeptical, so we're going to check it for ourselves. So again, we've got a left-hand side for that inequality. We'll plug x equals 1 into that left-hand side. When we do that, we get 8 minus 4, we get 4. That's the value of our left-hand side when we plug in x equals 1. Let's see what we get on the right-hand side when we plug in x equals 1. We've got, oh, pardon me, I'm jumping ahead, 1 plus 5. Of course, that's equal to 6. Now, they're not the same as each other, but all we need is that the left-hand side is less than or equal to the right-hand side. Is our left-hand side less than or equal to our right-hand side? Yes, 4 is less than or equal to 6. So we can draw our conclusion. Since the left-hand side that we calculated, 4, is less than or equal to the right-hand side we calculated, 6, and that's exactly the inequality we need, we know that x equals 1 is a solution to the inequality. So that's how we can check whether or not a particular value is in fact a solution to an inequality. But what if we want to know all the solutions? And there might be a lot. In fact, for that inequality that we just solved, there were infinitely many. So first of all, let's give a name to what we mean when we say all the solutions to the inequality. We call all of those solutions, that set of all those numbers, we call that the solution set of the inequality. So here's the big question. How do we find that solution set? Well, it turns out you can almost find it exactly the same way you find the solution to a linear equation. Okay? But here there's an important difference. And in fact, I want to just stick to linear inequalities at this moment. We'll solve nonlinear inequalities later in the course. It's pretty technical. We'll just stick to linear for now. Okay? Well, we're going to isolate the variable just like we would for a linear equation. Now, if you think of the steps that we do when we solve a linear equation, we add terms to both sides. Some of them involve the variable, some of them are constants. We subtract terms from both sides. Sometimes we do that. That's totally fine. We can do those with linear inequalities as well. Now, the final step we usually do is we usually multiply or divide both sides of our equation by a particular number. Okay, whatever the coefficient or whatever the multiplier is in front of our variable, we'll divide that out on both sides. Now, here's where things are different. If we multiply or divide both sides of our inequality by a negative number, a strictly negative number, then we have to change the direction of the sign. So this is a very important but. And this is true for multiplication or division. Okay? And again, we only need to worry about this if it's a negative number. So what do I mean by we change the direction of the inequality? I mean that if it was a greater than symbol, you'll switch it to a less than symbol. If it was a less than or equal to symbol, you'll change it to a greater than or equal to symbol. So we'll proceed just like we would with a linear equation, but if we need to divide or multiply both sides of our inequality by a negative number, we'll change the direction of that inequality. Okay, that's a very important detail that we need to remember. So let's take a look at some examples here. We'll solve the inequality, and then we'll connect this back to what you know about intervals of the real number line. But first, let's just worry about the solution. So if I look at this inequality, I see it looks a lot like a linear equation, but of course it's not. It's an inequality. It's a less than or equal to that's comparing the two expressions on either side. So, just like we would with a linear equation, let's bring all of the terms involving x to the left-hand side by adding 2x to both sides. And let's get all the constants over on the right by adding 5 to both sides. Now when we do this, it doesn't change the direction of the inequality. When you add or subtract terms from both sides of the inequality, it doesn't change the direction of your inequality symbol. Now my last step here that I'm going to do is I'm going to divide both sides by 5. Now 5 of course is a positive number, so when you divide both sides or multiply both sides by a positive number, again we don't change the direction of the inequality. So x is less than 11/5. Alright, now if I think about that solution set, okay, this is telling me any real number that's less than 11/5, and there are infinitely many of them, is a solution to that inequality. So let's draw our real number line. Let's put this important value on it, 11/5. And if I were to draw a picture of all the real numbers that are less than 11/5, well, I would not include 11/5. I want to be strictly less than 11/5. And it would be all the numbers that are out there on the left. So there's a picture on the real number line of all the x values that are less than 11/5. Of course, once we can draw the picture on the real number line, we can also give the interval notation. And so this is a nice, concise way of giving the solution set. So the solution set for our inequality is all real numbers less than 11/5. So we'd write that like this. Okay, we're going to exclude negative infinity because we always do. It's not a number, so it's never included. And we'll exclude the 11/5 as well because it's a strictly less than inequality. Okay, so we don't want to include 11/5. So that's the solution set for our inequality, and we've written it with interval notation. This is one of the reasons why we talked about interval notation, so we could use it to express solution sets for inequalities. Let's take a look at another example. Here we've got a greater than or equal to inequality. Again, let's proceed as we did before. We'll get all our terms involving x on the left. We'll do that by subtracting 10x from both sides. So I end up with negative 17x on the left. Now let's get all the constants over on the right. We'll do that by subtracting 13 from both sides. Oh, pardon me. We can do the calculation. It's negative 17. Now, again, we're just adding or subtracting terms on both sides. That's no problem. It doesn't change the direction of the inequality. But now we see an operation that will. We're going to divide both sides by a negative number, by negative 17. And that is going to switch the direction of the inequality symbol. So we're going to have not x is greater than or equal to something, but x is less than or equal to negative 17 over negative 17. That's positive 1. Okay, so notice again the change. And the reason we did this is that we divided by a negative number. On both sides. Okay, and this would also be the case if we multiplied both sides by a negative number. All right. Well, there's a nice algebraic expression that talks about our solution set, but let's draw a picture of it. Okay? Here's the algebra. Let's get a picture. So our important real number for this solution set is 1. And we want to include 1 this time, so I'll do a nice filled in circle there at 1. And we want all x that are less than or equal to 1. So that's all the x values that are out here on the left. Okay? So now that we see that, we can easily write in interval notation our solution set. We've got negative infinity to 1, and this time we'll include the 1. Okay? Because we've got a less than or equal to. X is less than or equal to 1. So again, just as a reminder, for inequalities, we can check solutions just like you would for equations. Of course, if we've got a less than or equal to inequality, all we care about is the left-hand side is less than or equal to the right-hand side. And again, we check them completely separately. Left-hand side and right-hand side, totally separate. When you solve a linear equality, like we did here, you proceed just with the same steps you would for a linear equation, trying to isolate the variable. But, and this is the important point, if you ever multiply or divide both sides of your inequality by a negative number, you must change the direction of the inequality. Okay? And we see here, once we've solved the inequality, we get solution sets that contain infinitely many real numbers, and the most efficient way to denote that is with a picture from the real number line or with interval notation. A nice, concise, and compact way to express that idea. All right. Thank you very much. Be sure to try some web work problems involving solving inequalities.